Okay, thank you. So I'm going to talk about the multi-threading in the Atlas high-level trigger. So the motivation, so by 2021, the LHC will be producing collisions at a much higher rate than ever before during its runtime. And even by 2026, Atlas's trigger will need to be able to handle an input rate of between 4 to 10 times the current maximum, which is 100 kilohertz. And using the predicted hardware specifications and budget constraints, the current multiprocess approach, which I'll describe in a minute, it will be insufficient. And also we need to account for the fact that the events are getting more busy, requiring more complex algorithms, and we will be introducing the ones that are currently running the offline software, which is the software we use in the wider analysis not during the detector's actual running time. So now what I'm going to do, I'm going to discuss the current Athena system, the limitations, then the Athena MT's multi-threaded system that will be running powering our analyses offline, and then how we are going to adapt this to include the features that they require in the trigger, and describe these features, and then I'll conclude. So Athena is Atlas's primary trigger offline reconstruction and analysis framework. It's a system of C++ libraries that are configured from Python or from a database. And Athena implements many of the components of Gaudi, which is an inter-experimental framework. Atlas uses this along with LXCB and a few others. In the traditional Athena sense, algorithms are run sequentially over each event. Data is passed via a singleton service termed event store, and each algorithm is implicitly dependent on the previous one. So you will, in a very simple example, you will have one algorithm running after the other. It accesses data the previous one has placed in event store. The system does not understand which algorithm needs to go in after each other. It's up to the user to simply place them in the correct order, and any problems will only become apparent once the execution is underway. Then once one event has finished, it clears all the temporary data, and it starts the next one, and so on and so on. This, of course, is oversimplified. A real job has 150 algorithms in 2,000 different dependency chains. So to exploit the multiple core revolution that occurred, we implemented a multiprocess approach called Athena MP. In this approach, each process executes on a single event sequentially, but we leverage memory sharing using the copy-on-write mechanisms, but this causes overhead. And algorithms for any given event are still processed on a single thread, and this is an approach that will not be tenable in the future, because if core counts continue to increase and the memory costs remain static, as it seems to be, the whole thing will become very memory constrained. So we are going to move to a multi-threaded approach to leverage all the memory savings we can possibly do. So Athena MT will use components of the multi-threaded framework Gaudi Hive. Athena MT will use the Intel Thread Building Blocks library to execute algorithms on all the available CPU threads. And algorithms using data from one event can be parallelized within the events, but also additional events can be placed in flight for additional parallelization, and we'll call that intra-event and inter-event parallelization. So in this example, there are not enough algorithms to run on each thread independently, so you will set off one and then start another event running on parallel threads, and when all goes well, you'll have perfect thread usage with no downtime. So the way we need to adapt the algorithm designs, as I mentioned, they're currently scheduled in a manually defined sequence. This would be very suboptimal for a multi-threaded environment, yet all the data dependencies must be respected perfectly. So Athena MT will implement a data-dependent scheduler. Each algorithm will have to be adapted to explicitly declare its dependencies, and we do this through a mechanism called data handles. The dependency graph is constructed and verified during the initialization stage, so any dependencies are then, any problems are then identified and presented to the user. The scheduler will create thread building block tasks to run the algorithms as their dependencies are met, and the Intel thread building block libraries will hopefully then minimize any idle time. So in a given example, the Athena scheduler will be aware of all the algorithms in a job. When their dependencies become available, the algorithm turns green, it gets passed to the Intel thread BB system, which then fills available threads. Multiple events in flight is the inter-event parallelization. So if, for instance, there are not enough algorithms to fill up all the threads, we can start processing the next algorithm. In order to cope with this, algorithms will need to be designed to be either reentrant or clonable, or if for a migration step, single algorithms may be permitted, but this could introduce additional idle time. And all our singleton services will be required to be thread safe. So in this example, you can have data entering these cloned algorithms here, or a single reentrant algorithm from different events at the same time, and they can all communicate with a thread-safe service. The Atlas trigger system has some additional requirements. So it has a concept called regions of interest, where only select volumes of the detector are processed to reduce processing time. We can the required volumes can be selected by data from the level 1 part of the trigger, and on average only about 10% of the entire volume of the detector is reconstructed in a given event. So it offers significant savings. But the goal for Athena NT is to migrate a lot of the algorithms used in offline processing to be working in the trigger as well. And the offline algorithms have been designed with different requirements in mind. For instance, all the algorithms are required to run at least once in offline, and all algorithms share data via the data store, and they're only isolated on the event level. While the online requirements mean that all algorithms must be run multiple times, and all algorithms must share data. And if you're processing a specific region of interest, the data from that region of interest shouldn't contaminate algorithms running in a different region of interest. So to give you an idea of the scale of the problem, we have 150 algorithms connected by 2,000 chains defining data flow and selection. We also have 400 tools, which are configurable subcomponents of algorithms, and 100 services, which globally acts, which are the interfaces to I/O configurations, and these all must be made thread safe. So by default, all the offline algorithms are unaware of region of interest. They process all the data that they can see. So to avoid this, without having to redesign all the offline algorithms, we've come up with a transparent method of limiting them to the required region of interest, and this is called, we've termed event views. So event views will implement a separate event store interface, and this separate event store will only provide data from the specific region of interest, and so the algorithms will not need to be altered to be aware of where they are. So in a given example, a creator algorithm will run in the normal event context. This will create event view stores within the primary store. We can see here, this is general event context. This spawns an event context here, so it spawns its own data store. It will then start running algorithms in this event context. These algorithms will only be able to see the isolated data store, and this can be done multiple times throughout the event. Once all the event views have finished, a algorithm in the event context can then merge the different stores back into the total event context. The trigger menu. The trigger menu is a list of conditions and the of which the event is accepted if any of the conditions are met. The high-level trigger performs reconstruction incrementally in a chain of steps of reconstruction and then selection of the data that's produced. Filter algorithms are placed in the chain to prevent execution of subsequent algorithms following a failed selection. This is important to save CPU time. And if no chains are left active, the event can be rejected immediately. And this is used in 99% of the events where it is rejected before all the algorithms have finished. So so control flow can be defined in like this, where we use these sequence and or parallel data structure command structures to create these steps. So you will have you essentially define step 1. This will then be passed within your MC, which will run the previous discussed process where algorithms where the dependencies are available get passed to thread TTB, which get passed there. And then once this criteria is evaluated, it will move on to step 2, provided the criteria are passed, which will then repeat the sequence. So this will provide us the control flow that the trigger requires to save unnecessary data processing time. So Atlas, to conclude, Atlas is redesigning its analysis framework to cope with the increasing data demands, and we're exploiting the trends in hardware. The trigger will be upgraded and its software to exploit this and unify the online and offline code bases, which should be a huge advantage to maintainability of the code. And we already have a basic set of algorithms that are functional, and the algorithms will be migrated over the following years. And we expect to have a first implementation of this by the end of 2018 and a full implementation running by 2020. Thank you very much.
So you said that the main reason for multithreading is the memory bound, but you didn't really explain why the multithreading reduces the memory usage. So I understand how TBB optimizes CPU efficiency, but I'm not sure why the memory consumption would be lower.
Well, there's a great deal of memory used in things like the magnetic field service, where the entire magnetic field is mapped in memory. And we have leveraged multi-process environments to do this, but this still adds overhead in its memory copying. So the objective is to get rid of that and possibly leverage other techniques like the reentrant algorithms to further reduce memory usage.
Different algorithms you have to do with this data dependencies?
Well, in the trigger we have, I think I gave them, I think it was 200 algorithms in the trigger alone, and then there are others in the offline that also need to be adapted. But this is underway. I think a lot of it is done. There are a few other modifications that need to be done as well. What do you mean? There's separate classes.
You have an algorithm where you have a loop also, and in your design you have more than 2,000 different algorithms.
The algorithms call tools, which can be called from different algorithms. Each tool can have the same code, but in the new system, each tool has to be copied so that it does not share data, so to keep everything thread safe.
Okay, then how many different processes or programs do you have?
Sorry, I've got the numbers somewhere on the slide, but this isn't working anymore. Okay. I think it was 200 tools in the trigger alone, and then, yeah, 150 algorithms, 2,000 chains, 400 tools, and 100 services. So services can be accessed from any algorithm at any time, and this is why they need to be redesigned to be thread safe.
I have a question about the ROIs. How do you deal with the overlap of the ROIs? And how do you choose the size of the ROI?
I'm sorry,
or how many there are? So how do you choose how many regions of interest there are, and how do you deal with the overlap between them?
I can't comment on that. That's out of my. I've just been introduced into this through the multi-threading.
So if you are redesigning the framework, are you also thinking about making it heterogeneous or not?
Sorry?
Making it heterogeneous?
Heterogeneous
Use
in what way?
FPGAs, GPUs.
Oh, we have a GPU prototype. At its current level of optimization, the benefits do not warrant its usage, in our opinion. But you can optimize to infinity with GPUs. So.
One rather technical question myself. You were discussing briefly the difference between making things reentrant and clonable. Did you study the performance difference between the two?
We don't have a large enough. I don't believe there's been any studies in performance differences. Obviously, the reentrant algorithm save memory, but then a given algorithm.
Because I was wondering about the cache caching. Because obviously, if you have reentrant, it lands on the same cache. You will have prediction of short-term constants potentially in the cache. So it might be interesting to. This is certainly highly depending on the algorithm, but it might be an interesting thing. Any more urgent questions? If not, let's thank the speaker again.